Okay. Thanks a lot for inviting me to this event. It has been extremely interesting so far, and so I wish to add my little bit of information and how this information can be useful for future instruments. So we have inline charisma and Athena, and hopefully also Arcus is an interesting idea that we hope it will go on. Okay, so let me try to go on with this presentation. Okay, here we go. Okay, so for people that don't do dust every day, although I noticed that there are many experts in the room, so then apologies for this basic information. So how is dust formed in the ISM, and why is it so important? The thing is that the dust accompanies the life and death of a star at every stage of its life. So we start from the star birth that happens, of course, with the collapse of a cloud of gas, but also dust. And what is remaining around a star, like a rotating star, is a system that will soon become a planetary system. So we have rocky planets like our own Earth and gaseous planets. And so it is extremely important to understand what are the elements in a specific, for example, in a specific place in the galaxy that are available to do different kinds of planets, because we know there are different flavors of planets out there. Then, as the star evolves, it becomes a red giant, and then the outer layers of this star are being restituted to the ISM. And this is where the dust recondense again, especially lighter elements like carbon and oxygen. So then this is another site of dust formation, especially silicates. But then we have to wait longer, and we have to have a more massive star to have a supernova event, where all the elements of the iron group should be formed. Of course, if we wait, long enough, and we wait, for example, for a neutron star merger, then we have all the other elements of the periodic table that they are also in solid form, even if we have only traces of those in the universe. And then all these elements are back in the ISM and ready to form a new star-forming nebula. So this is the cycle of dust, and then it becomes very clear why Carl Sagan said that we are made of stardust. Okay, so then stardust has been studied for decades now, and we definitely know a lot of it. We know that it is composed by vast majority by carbon in the form of graphite or amorphous type of carbon and PAHs, and silicates that are compounds formed by magnesium, silicon, oxygen, and iron by majority. There could be inclusions of also other less abundant elements. The dust sizes range from 1 nanometer to 0.5 micron. There could be exceptions to that. We can even have larger grains. And the dust can be parameterized in a simple way. The dust is distributed in size as a power law. And here in this equation, the n is the number, a is the radius of the grain. We know that the ISM dust is formed in crystal, for example, in the environment of AGB stars. But then the harsh environment of the ISM, think about cosmic rays, UV radiation, quickly make this dust not the structure of the lattice is not uniform anymore, but it becomes glassy to various degrees. So these grains are irregularly shaped and often porous. So we know a great deal about dust, but for example, there are still outstanding questions that we wish to investigate. For example, dust is destroyed at a much higher rate than is created. So if you put together the budgets of dust creation, but all the star sources, and the rate at which it is destroyed, we shouldn't observe so much dust as we observe. So we have to allow dust to be created also in other environments that are different from the immediate environment of a star. And also we have a lot of doubts about the chemical composition of the dust grains. For example, we know that iron should be more than 90% included in dust, but we are still not sure which form it should take. And besides, also other elements have an uncertain inclusion into dust, like oxygen, sulfur, carbon. So these are all things that we wish to investigate more. So this is where the X-ray come into play. The X-rays cover almost 2 decades in energies. And so this means immediately that we cover many transitions, both of gas and dust. So we cover the transition of nitrogen, oxygen, iron, neon, magnesium, silicon. We have seen that also in a slide in the previous talk. And we cover easily oxygen, iron, magnesium, and silicon that are all constituents of silicates. So this means that if we study dust in the X-rays, especially with the instruments that we have now, it means basically studying the silicate content. And also we have 2 prominent iron features that are elusive in the infrared band. But in the X-rays, we can have a direct access to those. So if we have access to both gas and dust features, we can calculate depletion. This is particularly straightforward for oxygen, for example. We are sensitive to a large range of column densities, say 3 decades in column densities. And since we use bright X-ray sources like X-ray binaries as background light, we can map all the galactic planes because they are naturally located all over the galactic plane. So what is the basic method that we use? This is actually very simple. We need an X-ray bright background source, and its light is modified by the dust and gas clouds along the line of sight, and we detect by means of high resolution, high energy resolution gratings, the absorption features. So here on the right-hand side, you see a detail of a silicon feature around 6.7 angstrom, so it's 1.84 kiloelectron volt, and you see how much substructure there is around this photoelectric edge. So all this substructure is due to dust, and we will see that in detail later on. Great. So this is the basic method. But so why is that? Sorry, let me go back. So why is that we have all this substructure here and not like a step function that would just indicate photoelectric absorption? So the reason is that when the X-ray comes into a grain, of course, a grain is very compact. So then when the X-ray will interact with any of the electrons, so will generate photoelectric waves that would create positive and negative interference with the neighboring photoelectric waves, and then creating a diffraction pattern. So the physics of that is actually very straightforward. And so this also means that depending on what is the electronic organization in the grain, you will have a different diffraction pattern. And so then this becomes the signature, the unique signature of the chemistry of the grain. So here on the right-hand side, we have a schematic sketch of what we should be able to see. So here is the step function that is the photoelectric absorption, so absorption cross-section on the y-axis versus energy. And here is an example on how this interference should work. And this is actually what we see in the data. So there was a problem up to some years ago that even if with Chandra and XMM we would detect this substructure around the dust features, there were no models able to interpret those. So what we did was a large campaign, measuring campaign using the Soleil synchrotron, SRF, and electron microscope, especially the one in Cadiz, to measure all the different edges. Of course, you know that every beamline is specialized around a certain energy range. So that's why we need to cover the whole X-ray range for the same set of samples. We needed to go to different facilities. So we are quite advanced, and we are creating like a global model to be implemented in XSpec and SPECS in preparation for the launch of Charisma and later on of Athena. So we are studying all the different edges. Some work are still in preparation, and some others are already published. So if you are curious about that, please check those publications. So for today, I only have the time to focus on the silicon edge that we briefly saw before. So this is how a synchrotron beamline experiment would look like in the raw data. So on the y-axis, we have the intensity of, in this case, fluorescence. And is a measure of your absorption cross-section as a function of the wavelength. So you see that the secondary peak here all have different substructures depending on the sample that you have. And many, if not most of those, are detectable by our the resolution that we have right now. Okay, so let me remind you how, before this campaign, we would fit our data. So this is the dust edge with all the complexity, and here is a step function. So you clearly see that you miss everything about that. So, and you also are assuming that everything is absorbed by gas, which is definitely not the case. So this is the new way. So gas is relegated to the here like a very a modest contribution to the total absorption, and all the rest is fitted by dust, and with quite some accuracy. So let me go a little bit in detail. So here these absorption peaks really tell you about the chemical composition. Because about what we have seen before about the diffraction pattern. And then the sharpness of these peaks can tell you about how crystalline this dust is. Because of course, if you have like a disordered lattice, then the absorption won't be so sharp. It will be much more smooth. And so the sharpness of the peak tells you about the crystallinity. And last but not least, this pre-peak that you see that is an apparent absorption, but in reality is a scattering peak, tells you about the dust size. Because this peak changes intensity depending on what your dust size distribution is. Okay, so the future. So here on the left-hand side, you have like a summary of what we hope to see flying soon. And the plot here is on the top panel. We see all the elements that can be interesting for dust studies. And here in the diamonds are the elements that we can study now with the current instruments. And the triangles are the ones that we will focus on in the future. Great, so carbon will be covered by Arcus if Arcus will ever fly, while all the rest will be covered by Charisma and Athena. So here is the energy range where these missions will have, the most impact. Great. So what does this mean? It means that in the future we will be focusing more on dense environments where the column density is such to enhance high energy absorption features. So we are talking about sulfur, calcium, even titanium, iron K absorption features, and so on. All right, so let me give you some examples. For example, we will observe, of course, silicon K. This will be like a piece of cake. So this is a simulation with Athena. We see that the distinction between two chemical composition will be straightforward to do, while now we need longer exposure times, very high statistics. So here with Athena will be an immediate exercise. Then we have here on the right-hand side a plot on the iron K. And iron K is an absorption feature that will be enhanced only if the column density of the dust along your line of sight is of the order of 10 to the 23. So we are talking about regions near the galactic center towards molecular clouds. So very difficult regions to reach with other wavelengths. So here you see a comparison among different models, and you see that Athena will be able to distinguish among those, really determining the chemistry of iron in those regions near the galactic center. Other edges are, for example, calcium, that are right now are totally inaccessible because of signal to noise and resolution. Calcium is supposed to be to reside in the very center of silicates, together with aluminum, for example. And on the right-hand side, we see sulfur. Sulfur is supposed to be very, very lightly depleted in the ISM, but is a very, very important element, for example, in rocky planets. Planet Earth is rich in sulfur, and of course you want to get sulfur from somewhere. And in the molecular clouds, we only have traces of molecules in sulfur rather than iron sulfate that we hope to see with the Athena measurements. Great, so let me get to the conclusions. High resolution X-ray spectroscopy plus reliable laboratory measurements allowed us to have an incredible leap forward in our understanding of interstellar dust. Of course, there is still a lot to do, so exciting times ahead, and future instruments like CRISMA and Athena will explore for the first time the densest regions of our galaxy. Thank you very much.
Thank you very much, Elisa. So I think there are some questions. From Karine Demic. Would it be possible to get some information on the carbon-rich dust with Athena, despite the fact that the C-band is not observable?
Well, you can get, in principle, say, indirect information. For example, you want to know if there is silicon carbide. Then what you can do is to observe the silicon edge and understand if there is silicon carbide. So in this way, you have information on carbon. So this is indirect information. Direct observation of carbon is, of course, tricky. And so carbon is not really, the strong point of this mission.
Okay. There is also a question by Jérôme Petit. The scales of the features are a few percent. What will be the accuracy of the calibration of Xifu, yeah.
Well, this is all, things to be seen, of course. Those regions, for example, it all depends if there are these elements in the instrument. For example, silicon, for example, in CRISM, there won't be, discrete features of silicon. So this is definitely an advantage. So in studying silicon, while for Chandra, it is right now a problem, something that you have to calibrate very carefully. And other regions, hopefully, will be in smooth places of the effective area.
Okay, thank you. There is the last question. Why X-ray scattering never observed on XAS data taken at the lab?
Say it again.
Why X-ray scattering has never been observed on XAS data taken at the lab?
Yeah, this is a good question. It depends on, I think it depends on first the modality of how you observe it in the lab, and the density of the sample that you use in the lab that doesn't allow scattering.
Okay. Thank you. So thank you very much, Elisa.